All right, here we have homework 4. This will be part A. So as you can see, we have two tanks right here. We have tank 1, tank 2. These are both spherical tanks that are open to the atmosphere. And right here we have a pipe connecting them, labeled A12, which is 0.2 meters squared. And then we also have an outlet pipe for the second tank with an area of 0.2 meters squared, same as the first one. The heights are labeled right here with respective 5 meters and 3 meters. And the that's the initial steady state of like where the water is. And then we have radiuses for the first one being 4, radius for the second one being 2. And then our QN for 1 and 2, which is the inlet flow, is equal to the area of our pipes going out times the velocity of the amount of liquid going out there. So we will start with deriving the steady state equation for the inlet flow. So we are going to be using a problem similar to this, not the exact same, that is going to help us solve for this. So in the one that we will be looking at, we have a rectangular tank, which water level is still labeled H. We have 2 points in here. We have 1 and 2, Z values, and it has an outlet flow as well. So the equation we will be starting off with is P2 minus P1, and this will be all over density is being added to acceleration due to gravity times C2 minus Z1. These are just our initial states, and excuse me. All right, so then we have plus V2 squared minus V1 squared, and that is going to be over 2. And this will be all equal to 0. So since the cross-sectional area is so big, our V1 can just go away. We don't have to worry about that. It becomes 0. And then our positions, our Z2 minus Z1, that will become 0 as well. So after a little bit of rearranging, we get 0 minus pressure, times acceleration due to gravity times height. This is over the density. And this is being added to a little section over here, V2 squared over 2. And that is equal to 0. So since we are solving for V, we can do a little bit of rearranging, and by adding this over to the other side, multiplying by 2, and after that we get V equaling 2GH. So since our problem involves two different tanks, we have to rewrite the equations a little different. So we put the V in here into these Q equations. So we'll get Q 12 equals A 12, and this is being multiplied by what we solved for here, our V. So we have square root of 2G, but remember we have two different tanks, and instead of 1, just like our example, our extra little problem shows. So we have to have the difference in our heights. So we'll have H1 minus H2. And this is going into absolute values because we cannot have a negative under the radical. That will just cause many different problems. So our Q2 is slightly simpler just because we don't need to worry about the change in height. So our Q2 is equal to our area 2, and this is just times 2GH, no difference in height. So there we go. That is part A of homework 4. I will see you in the next part. So here's part B, and in this part we are going to be deriving differential equations to solve for the time variation in the fluid height in both tanks. So as you can see here, I have the equation that we got from part A. I just changed it up a little bit and put it in terms of dV over dt. So we're going to have to change this around a little bit. We need to compensate for the sign, since if it's negative, it would really mess up finding the stuff under the radical. So to do that, we rewrite this as dV1 over dt is equal to our inlet for tank 1. And the difference now, we have SGN, this being subtracted from SGN, which is just sine. And in here, similar to like our absolute values, we have our H1 being subtracted from H2. And this is really the only difference in the formula that we have, so we can keep the rest the same. So this will be minus, or being subtracted from the area of the pipe, the area of the pipe between the two, being multiplied by the square root of 2g. And then in our absolute values, H1 minus H2. Alright, so we are also able to do this for our second tank. So this one is a little slightly different. I'll explain it a little bit more as I'm writing it out, but it starts off as the same. So dV2 over dt is equal to, and now obviously since we are on the second tank, we are talking about the inlet for number 2. So Qn2, and we obviously keep the sign thing because it matters with this one as well. Can't have a negative. And same as the last one, H1 minus H2. And then same as the first one, we are subtracting A2 this time. Or I'm sorry, no, it's still A1, 2. And being multiplied by 2GH. But our H is a little different because there's a difference in height and we can't have a negative. And now the part that really makes this different, granted there were some little differences such as like the variables that we used, we have to subtract the flow rate out for the second one because that's where the water in our case is leaving. So we have A2 area of the second pipe, the outlet pipe, and that is being multiplied by 2GH. But since there is no change anymore, the H is just the height of the second tank. So now we aren't 100% done. There's a little bit more that we have to do. We have to change from dt, or like in terms of dV in terms of dH. So we have our little formula right here where we have dV over dt is equal to the cross-sectional area, and this one is held constant. The only reason it's held constant is just because we're doing that for right now. Normally it would not be held constant. And then that is multiplied by dH over dt. Ooh, sorry, that was a little bit big of a T there. So, if we go ahead and change these values to dH over dt, our formulas are still going to look exactly the same, except for the fact that we will be dividing by the cross-sectional area. So I can go ahead and write that out right now. dV1 over dt Oh, I apologize. We were on dH because that's what this allows us to solve for up here, right here. So dH equal to everything stays the same, nothing changes. So we have our Qn 1 minus. Let's just get rid of that. minus the sign, because negatives are important. And this is really only used if the flow rate is negative. Otherwise, it really won't have that big of an effect. This is also being subtracted from A12, A12, and then in our square root we have 2, G, our difference is in height, H1 minus H2, and then like I said, so we just take this, and it gets divided by our AC, the cross-sectional area, which is different for tanks 1 and tank 2, so they have their own cross-sectional areas, so it'll be AC1. And now moving on to our second tank, dH2 over dt. And similar to the first one, we're just going to keep the exact same thing, what we have right here. Only difference, dividing by AC2 this time. So, go ahead, we got our inlet. And making sure we keep track of the signs, because negatives can be scary in this situation. Ooh, minus, not multiplied. That would really screw this problem up. So, just rewriting what we have. And then just a little reminder, this one is slightly different because we have to take account of the outlet flow. So that's what our A2 times 2GH is. And there's no difference in height because it's the last tank. And like I've mentioned many times, all of this is being divided by AC2. Alright, I will see you in the next part. Alright, so here we are on the on the continuation of part B for our problem. So here I've drawn a circle kind of resembling our tank. And I've labeled the R's right here. I've also drawn the little cross-section thing we have up here where it is equal to the height of our liquid in the tank. And I attempted to draw a little dotted line here to represent this triangle. So this triangle, as we can see, obviously has a hypotenuse of R, and one of the legs is the top one will be RT, radius times the time. And the height right here, or well, not the height, I guess the height is going to be h of t, but it's going to be subtracted from r, obviously because radius is right here. Makes sense. So we're going to use the Pythagorean theorem now to get ourselves a little equation. So, as we all know, r squared is equal to rt squared. And that is going to be added to our ht minus r and squared. So our goal here is to solve for RT. So we can do a little bit of rearranging, and when we do that, we will have R sub t squared is equal to just our normal radius squared minus our height. So, since we know that cross-sectional area, denoted as AC for a circle, is equal to pi r squared, we can do, I'm sorry, in this case, it's not pi r squared. In our case, it's pi rt squared. So we can do a simple little, putting the rt in here, and we have our cross-sectional area being equal to pi redraw that. Pi times, and now we plug in our RT, so we have r squared minus, and then brackets, r h of t minus r. That squared and end parentheses. So, as you saw from the last part here, when we solved for our DHs, we found that we have to divide it by the cross-sectional area of 1 and 2. So, now we have our cross-sectional area right here. So, all we have to do is just pull these equations back into play and change out the cross-sectional areas. So, we'll start with the first one. And I'm going to do this one a little different now that, you know, it isn't just one variable. We have a long written out formula for it. So we'll go back to our previous, and we had Q in 1 minus our sign. We always have to make sure that it's positive, so no mistakes happen. And then remember, this is being subtracted from the outlet. And that is being multiplied by 2g h1 minus h2. And now, as I mentioned prior, we are dividing by the cross-sectional area, so we'll just go, and it's either cross-sectional area 1 or cross-sectional area 2. So for this case, it's going to be pi, beautiful little character there, being multiplied by, since this is for the first tank, r1 squared, and that is being subtracted from our h1 minus r1, and still stays squared thanks to the Pythagorean theorem. So there's our first one, and now we move on to the second tank. So second tank is going to look extremely similar, with the only difference being the outlet, as mentioned in the previous, this being the only change that we really need to worry about. So, got it equaled up here. Make this one a teeny bit longer, and actually I'm going to start with the bottom here this time. So we have our pi being multiplied by the second radius, and that is obviously squared, and that is being subtracted from, let's just fix up that 2, and that is being subtracted from our h2 minus our r2. All of that still squared, and parentheses, and top, simple, gone through it a lot. Got our q in, it's time for 2, minus our sine, h1 minus h2, and that again is being subtracted from a12 connector pipe, the area of the connector pipe, being multiplied by 2g h1 minus h2, and we also have to, as I mentioned previous, have to take into account the outlet for the second tank, and obviously this one has no change in height, so it's just 2gh2. And there we go. There are our final equations for the time variation in both of the tanks. Thank you very much for watching, and I will see you with coding for part C.